Today, we're happy to have Asher Berlin, who, this is sort of an exception. Normally, we only allow CCPP members to give the brown bag. Asher has not been a member for almost a month.
Yeah.
Because now he's at Fermilab, right?
But he's a visiting scholar.
He's a visiting scholar.
Am I really? I didn't know that.
Yeah.
Yeah.
That's how you
Well, you
get
are
it.
visiting and you are a scholar.
Yeah, that's how you get in the building. It's their justification for that. Anyway, he will be talking about a step in understanding of the Hubble tension.
Yeah, thanks. So this is based on.
Oh yeah, just to hear that.
Everything good?
Everything good.
This is based on this recent paper. A few weeks ago. Archive number, if you want to look at it, is with Daniel Loney, postdoc at BU, Melissa Joseph, actually ran all the simulations, all the code that I'm going to be telling you about today. Who's a grad student at BU, Martin Schmaltz, and Neil. Everybody knows Neil. Okay, so this is a new idea to resolve the Hubble tension. So I'm assuming that most of you are either intimately familiar or probably have heard of it at some level. So let me just give a kind of a basic overview. I think hopefully to cover most of the things that are required to understand what I'm going to be telling you about. So, quick recap of what Hubble's law is. What is the Hubble parameter? This is a statement that, let's say you have two objects that are initially some distance apart, some distance d apart, due to the expansion of the universe. This is a function of time. Okay, and this expansion rate is encapsulated by so-called Hubble parameter. It's defined to be the time variation of this distance over this distance. And here you see I've used the symbol H naught. That just denotes the value of Hubble today. And Hubble's law states that, at least for objects that are close to us, their redshift is approximately just given by H naught times d. So if you see some distant galaxy, let's say it's a certain distance away, you take H naught, you hit it by that distance. This tells you what the redshift of the galaxy is or how fast it's moving away from us. This is the redshift of light. Okay.
And you're working in C equals 1.
Yeah, that's C equals 1, right?
So this is the redshift, or essentially just like delta lambda over lambda, looking at some wavelength of light. In many instances, this is trivial to measure. You look at hydrogen lines, see how they get shifted away from where they're supposed to be. This tells you the velocity of recession. Okay, the fact that the universe is expanding means that if you look around you, all these galaxies seem to be moving away from you. This becomes more and more true as you look out the larger distances. So this is just a distance to some source. And this is very difficult to measure.
And ill-defined, if you ask me.
And ill-defined. Well, we'll talk about
Because you have to say whether it's angular diameter distance or luminosity distance or proper motion distance, etc.
Agreed. So the basic statement, though, is if you can measure the redshift of some galaxy, which is something trivial to measure, and infer its distance, and I'll be talking about different distances that make sense. Those two quantities allow you to determine H naught. And of course, this is only strictly valid for redshifts much smaller than 1. This is a leading order term, but if you go out to higher redshifts, this story doesn't really change. This just turns into an integrated version of this equation. Okay, so all the magic is in here. Okay, so that's what the industry is really about. So let's talk a little bit about measuring distance. And I should say, some of the details that I might get into or hint at here, I'm not an expert in. This is kind of a new subject area for me, but I'll do my best to give a description of certain experiments trying to do different things. But there are 2 different main classes of distances that you can measure. Okay, so one idea is the luminosity of some object. So imagine that you're an observer. There is some source, okay, that's shining a distance d away. And the basic point is you want to look at some source whose intensity, let's call it I naught, is known for some reason, okay, due to some known physics. This is what's called something like a standard candle. If you can look at an object that has a known intensity, and you measure, let's say, its intensity where you are, so this is measured. This is a cartoon explanation of one class of distance measurements, just looking at apparent luminosities of objects. There's also at a similar cartoon level, just looking at angular sizes of things. Okay, so once again, if you're an observer, let's say you're looking at an object, actually resolve its size, and let's say this this size d subtransverse is known. Some quote unquote well understood physics. And if you can actually see that, able to infer, measure an angle, okay, just from basic trigonometry, this thing is measured. This is measured, this is known, you can infer d. Okay. So these are 2 classes of observations to infer the distance of something. I'll be talking a little bit more about specific observations and specific objects. But let me just go back to here and actually talk about what the tension is. So I told you earlier that you can measure H naught because you can trivially get the redshift, and if you can infer the distance to some object in some way, that can allow you to determine H naught. So what is the H naught crisis?
Crisis.
It's a crisis.
Okay. I had not been aware it had risen.
Yeah.
in-
Oh yeah.
Okay.
Hang out with more particle physicists. We have lower standards for price.
Okay. So the basic statement is that direct measurements of Hubble, like the ones that I was just telling you about, are discrepant with values inferred from the early universe. I'll talk about what that means. This will be like probes like measurements of the CMB or the VAO by about roughly 4.5 sigma. If you're assuming lambda CDM, okay, and I'll show how that comes in. The basic statement, once again, is that in the early universe, this includes probes like measurements of the CMB, the VAO. It gives values of H naught around 7.5 plus a half. kilometers per second per megaparsec. This is inferred.
The definition of early here is 0 or the 1, right?
Sorry?
Your definition of early is 0 or the 1, right? So because BO is pretty.
Sorry. Yeah, BAO is like is galaxies at low Z, but really when you look at the BAO and to infer an H naught, you have to assume some early universe cosmology. So really what I mean by early universe is you're sensitive to let's say you're sensitive to H of Z going all the way back to recombination. So although BAO is a low Z probe, they're assuming lambda CDM up to Z of 1,000.
And so that gives you an H of Z for all Z's, say from 1,000 down to.
Yeah, I mean, so
zero.
if you're assuming lambda CDM, you essentially have this function.
Yeah.
That's right. And I'll be coming back to this in more detail, but because this is kind of the more standard story for, you can look at CMB and I'll describe how that comes about and for an H naught. A lot of the discrepancies have been coming at the level of the late universe. So let's talk about late universe. I'm going to be coming back to all of this. This is actually the main point of the paper that we talked about. Hopefully I have time. The late universe. Well, let me just give you a little bit of a flavor of a few things. One interesting class of measurements have to do with supernovae and the distance ladder. Okay, so the basic method here is we're going to use classes, not we, other people are going to use classes of objects that are standard candles in this sense. Due to understood physics, have some understood absolute intensities. So these are things like Cepheid variable stars. These are stars that dim and brighten over order of days with a period that's correlated with the absolute luminosity of these objects. There are other kinds of stars called tip of the red giant branch stars. So these can be calibrated, for instance, meaning you can infer their actual distance, ones that are very close by, just via parallax. Okay, so if these things are very close, you can look at the position of the sky in the winter or the summer, see how the position changes, and for their actual distance. Once these things are calibrated, the nearby ones, you can use these objects at higher distances, for instance, to calibrate supernova. They're very bright, allowing you to go out to higher distances. And this gradual sequence of using close by objects, using this to calibrate objects that can take you further and further, is what's called the distance ladder. Okay, so this, once you calibrate, let's say, the physics of supernova, you look at a supernova that is very distant from you. Now that you have calibrated in terms of its absolute magnitude, this allows you to infer some distance supernova. And because you inferred the distance, that's the stuff that you need to measure H naught. So that's
So what's the meaning of parallel here? Do you mean it's the different stars all in the left side?
like as the Earth is orbiting,
Yes.
as the Earth is on its orbit, Earth's over here, Earth's over here. The apparent position of a star as the Earth is orbiting
Oh,
shifts in the sky.
oh,
And if a star is close enough, you can actually see that.
Mm.
Then you can, just from trigonometry, you can infer the distance of those things. But for that to work, these stars have to be pretty close. So that's always the first step in building up a ladder. So this is the standard story for things like supernova. And I'll tell you a little bit more about that.
Are you going to comment on the systematic error that's inherent in this procedure? I mean,
I'm not, I will probably say the word systematic once and move on.
you calibrate with something nearby and then you extrapolate to
Yeah,
things that are not only
yeah.
far away, but far back in time.
Yeah, that's right.
So
So there's of course a systematic, and if you're someone like Tim Reese, you get attacked at every step of your distance ladder over the past 10 years. And what happens is typically that people keep attacking his steps in the distance ladder. And of course, there's systematics associated to all of them. You have to combine it. He goes away, squirrels away, comes back and tells you he understands the systematics even better and gives you a measurement that has even smaller error bars than what was before. So there's a
That does happen, but it is worth noting there are other distance ladders people build
yeah,
that are not in agreement within the error bars.
that's right.
Right.
That's
So
right. So
it's not the shoes measurement is not the only game in town.
That's right. And so I haven't even mentioned, I'm about to mention shoes.
Yeah, but it has to be said, I mean, if you took the ensemble of credible values, it's almost a continuum. So to say that it's 4.6 sigma is really taking the extreme values, I think, right? There are many, many new methods that come down sort of in the middle.
There
So
are.
there may not
there's
be a
some, not-
crisis at all, but still it's interesting to think about. There might be. So
Right.
I don't think you should mislead people into thinking there's actually a crisis observation.
I
at this
I
point.
don't know that I totally agree with that. I mean, like, there's Holy Cow. Holy Cow is pretty comparable. You can do the tip of the red giant as we were discussing, which recalibrates the supernova down. But a lot of these early universe measurements, when they're really early, when you just take the early universe measurements, are pretty consistently, maybe not 4.5.
Like the analysis of ACT and the combining ACT and WMAP is giving a value more in the middle, and Holy Cow is the one with the strong lensing, right?
Yeah. So like
Those have huge error bars, of course, but I just think that one shouldn't insist that there's a crisis. It can mislead people. There may be a crisis. A crisis may become established, but at the moment, they're so. What are you laughing at?
The camera's not pointing the right direction, but Asher erased the word crisis.
Oh, okay. Thank you. Now I'm happy. Now I'm happy. It's a very interesting thing to think about, because the more there's a credible idea of what could give rise to a discrepancy, the more.
Yeah, I'm gonna talk about the full suite of measurements, of late time measurements and early universe measurements. And so I think, it's definitely the statement that, so I will mention shoes and Adam Reese's group, and they are one measurement. There are other late time probes that I'll discuss. And there is a scatter, but it's definitely the case that there are several measurements at late times that all kind of agree with very large values of H naught. And most early universe measurements agree. And
Wait, is your talk, I assumed your talk was about some theory model that was going to explain it. But if your talk is really about the observations, then you're going to address this question that I was raising. Which is
well,
it?
I'm gonna go through the observations very quickly, just to assuming that most people haven't heard about them in detail. But the
It's a
main point is
review, but that's what I was assuming. I just wanted to maybe moderate the terminology a bit. Okay.
that's fair.
Thank you.
Thank you. Okay. So yes, so along these lines of supernovae, one we just heard a little bit about. The group using Cepheid variable stars. She's collaboration, Adam Reese, others. And they calibrate their supernovae with Cepheids, and their current measured value that they quote to date, very roughly here. Okay. I'm assuming that most of you probably already know this, but just to remind you or tell you, these guys are using objects in a limited redshift range, roughly like 10⁻² to 10⁻1. This is because you go to things that are too close to you. The peculiar velocity of these systems is larger, which is typically on the order of a few 10⁻³ If you go out to too large of a redshift, there's some additional model systematic, and that you're really measuring H of Z, this integrated quantity, as opposed to just H naught. So you want to use objects that are close to you, but not too close. It's really the Hubble flow dominating the motion of these objects. Also mentioned, there are other measurements. So this is slightly a slightly newer way. So this is slightly historically has been kind of a more traditional approach to calibrate these things. More recently, people have started discussing a different class of stars called the tip of the red giant branch stars. There's a scatter amongst these. So fair enough, I'm just going to drop this unit. I'm talking about H naught, but everybody knows what I mean, just to save some writing time. So one group reports a measurement of around 70 plus or minus 2. Okay, this is Andy Friedman and others. There's a couple different reanalyses of these kinds of stars in this kind of method. Those gotten 72 plus or minus 2. There's another analysis that gets 75 plus or minus 2 with these same objects. Perhaps not super surprisingly, these analyses are slightly correlated with this author list here.
By the way, I think it's Wendy Friedman is Freedman. I think that's the paper you're referring to. The Chicago group.
Is it like that?
Yeah, right.
Sorry. Yes.
And
So-
what these are the same 10 minus 2, 10 minus 1? The values of Z.
The values of Z. I think so. That's kind of a generic reason. You have to. This is typically a hard number you want to obey because 10 minus 3 is the typical peculiar velocities of stars. You can go up to higher Z, and I think that's a choice of any collaboration. But the higher Z you go up to, now there's more knobs that come into play and what model you're assuming.
I mean, it's the same supernova, right?
Same supernova.
It's the same supernova. It's an earlier, it's
Oh,
that
sorry,
earlier
between
step
these things.
in
Yeah, these
the
are just different
ladder.
calibrations.
So it's replacing Cepheids with the
Yeah,
circumference,
sorry.
right? But it's the same supernova.
Yes, sorry. That's what you meant. Exact same ones.
What about masers? Or they're not?
I'll get there as well. Actually, some of these in building up the distance ladder, masers are sometimes used as part of a calibration process to calibrate supernova to go up higher. And they're also just maser analyses on their own. And I'll mention what values they get as well. So there's a bit of a scatter with tip of the red giant branch. These are just different ways to calibrate the supernova and build up the distance ladder. And there is some systematic, obviously, and there's probably some systematic in here. Okay, so the basic statement is these measurements, perhaps this one, which is kind of sitting in the middle between early universe and the Reese value, are kind of agreeing with larger values of H naught. Just for honorary mention, I was planning on going into a little bit more detail, but just for the sake of time. Yeah. Okay. For the sake of time, let me just mention other things. There's strong gravitational lensing. Holy cow group. They get a value around 74 plus or minus 2. These things have large systematics tied to them, coming from modeling of lenses that are doing the strong gravitational lensing. Megamasers. These are not completely decoupled from reset all. These masers are in fact sometimes used to calibrate the building of this ladder. These are astrophysical masers that, due to their well understood physics, have should have a certain size, and you can actually observe the apparent size of these objects on the sky. Okay. That's around 74 plus or minus 3. Another one that's quite interesting as well are gravitational waves. These are too early to really say anything definitive. There are very few objects. This might be slightly outdated because I haven't looked at the new analysis yet, but as of a few years ago, this was around 70 plus or minus 10 because I just had very few objects. But this is a very interesting method to go after values of H naught. The gravitational waves of things like neutron star mergers with an optical follow-up that might be important in the future. So that's what I wanted to tell you.
That's not a continuum, but it is a discrete one.
measurements next year. You can see this is kind of sitting in the middle, but aside from that, any other ones you choose, this one doesn't really mean too much. There seems to be something. And what we've chosen to do is just ask, how hard is it? So this Reese value, let's just take it. How hard is it for early universe to be consistent with those measurements?
But it is interesting that the high Z values or the whatever are entirely angular measurements. They involve only angular measurements and initial conditions, whereas the high statistics, low redshift things are all luminosity measurements. So it is interesting that kind of conceptually they're different distance measures.
I guess aside from this, this is I think here you're inferring this is more of a triangulation here for mega majors.
Yeah, it's not exclusive. It's not exclusive. I'm just thinking that in the large numbers.
Yeah.
But you're right.
That's right.
Is holy cow also luminosity distance or?
It's timing, so it's in a weird different state.
It's something else.
But it's more like angular, I would say.
Right.
Yeah,
That's right.
yeah.
You have some source that's like varying over the order of months. And the strong lensing, these images have a little blip. And you can model the lens and you can reconstruct all these distances.
You have a section in your paper, right, David, about what that distance is?
Yes, technically there is a section in the paper about it, but it's a little hard. But I mean, the real question is the luminosity distances involve this phase space density of photons, whereas the other ones don't. And so it is kind of interesting, especially from a particle physics perspective, to think about the point that if you involve the phase space density of photons, you're assuming something about space-time, something additional about space-time beyond geometry and special relativity, or Lorentz, beyond Lorentz.
Okay. Thanks. So what I want to tell you about next is how can you infer this value from the CMB, just more generally early universe probes. The statement is that as observers of the CMB, what is done is you're looking back to the last scattering surface, what I'm abbreviating as LSS, just when photons were liberated. Okay, and there's some distance, some conformal distance to that last scattering surface. There are photon fluctuations on that surface with a characteristic size that I'm going to denote as R sub S. This is the so-called sound horizon. Physically, think of this as just the maximal size that photon perturbations could travel up until the time of recombination. Okay, so these are photon perturbations here that and what's measured from CMB measurements are angles. So from this characteristic, this is more like a standard ruler in a sense. If you, assuming a model, you can calculate the size of the sound horizon and also calculate the distance to recombination. And what you measure are angles. Okay, so roughly just this, where specifically what the sound horizon is, as I was saying before, is the conformal, usually the conformal distance that a sound wave in the photon baryon fluid can travel from arbitrarily early times to the time of recombination, where this is the speed of sound in the photon baryon fluid, which is roughly that. Okay, you can rewrite this in terms of redshift, let's say. The redshift at recombination is known to be at around 1100. In terms of redshift, roughly there. So this is how you can see Hubble entering at early times. So this is only redshifts before recombination. What's going to dominantly contribute to this is radiation and matter. And the distance to the last scattering surface is similarly just the distance between redshift 0 and recombination. That conformal distance is roughly that. Because this is late time, okay, so this is dominantly contributed by dark energy. And yeah, in terms of the energy density contributing to the expansion rate. Now, when you look at, let's say the temperature power spectrum of the CMB, you see these little peaks. These peaks are roughly spaced at L. They have some overall phase, but the spacing is at L is roughly just controlled by the sound horizon here, theta S. Okay, or this is L. So the spacing in L of the peaks of the CMB, this is some phase, and I'll be coming back to this. For instance, neutrinos contribute to the space in the standard model. This spacing in L of the peaks is very well measured. In lambda CDM, the reconstructed value is roughly 10 to the minus 2, 10 to the minus 6. So it's measured roughly to 1 part in 10 to the 4th. So how could you imagine having deviations from lambda CDM? Let's go back to this diagram here that I drew. Surface, little photon perturbation, characteristic size RS. Okay. Now let's extend this out even further. What we measure are angles. So an equivalent story that's possible is that this is actually RS, or this is actually RS. So you can see there's a degeneracy. You can slide this around. We don't truly know the size of RS. We can predict it, assuming a model. But you can leave the angles fixed, really the spacing of the CMB, by scaling, for instance, distance of the last scattering surface and the conformal size of the sound horizon. So what we want to do, like I told you before, if you have a model, or you want the cosmology to be consistent with a larger value of Hubble at late times. What's dominating at late times? At very late times, it's dominantly dark energy. So let's say you dial up dark energy in your model to predict a larger value of H0. This is going to decrease this integrated quantity. This is going to decrease the distance of the surface of last scattering. So that is starting from lambda CDM right here. This is pushing you that way. Okay, so delta H0 greater than 0. But to be consistent with this angle, you want the sound horizon to be smaller by roughly 10%. And you can see this means I want something like, if I had a little bit of extra radiation in the early universe, that would contribute. Or I know I'm messing up the camera. That's all right. So get a little bit of extra radiation that can contribute, that could shrink the sound of the sound horizon, contribute to Hubble at early times. Okay. So if you ask, let's say, how do I go from 68, which is roughly the predicted value in lambda CDM, to 73? This could be done, for instance, in principle, if you allow the effective number of neutrinos, effectively controlling how much radiation energy density there is aside from photons, in the early universe to move from 3, which is the lambda CDM value, to roughly 3.5. Okay, so this is an extra radiation.
Sure, to understand kind of the story better, because there is also BO, right, which is on one side is sensitive to RS,
Yeah.
but on the other side it's also sensitive to late universe, right? So when you play this game, then it will change CMB and BO differently, right? And as far as I remember, they're pretty consistent.
They're consistent. I mean, if you're dominantly changing, like let's say the CC component,
Right.
The distance to whatever distance is important for BAO, and the distance that is important for CMB to the surface is dominantly just scale like 1 over H0. So they scale in the same way. They're not right. Okay. They're not exactly the same, but they scale in a similar way.
So I mean, the CMB only constrains H naught at all if you assume the universe is flat,
That's right.
and specifically lambda CDM. So I think the contribution of the BAO is really like, I think I'm maybe repeating what you're saying, but it's this later time stuff. Well, it's the flatness plus whatever dark energy can do gets tamped down by the BAO stuff. So if it's just CMB, you can monkey with all that stuff and get H naught of whatever you want, like literally whatever you want. You do BAO and then you're like, oh, the universe has to be flat. Things look like a cosmological constant. And so all those assumptions in your CMB analysis are good. I think that's the way those things fit together.
And another way to say it too is, although the BO measurements are low Z measurements, the distance that what you're sensitive to really is the distance to when baryons decouple from photons. So it's typically much higher Z. And so it's involving the same kind of standard ruler as the sound horizon, that same thing it prints on the 2-point correlation function for BAO. And BAO is really a tracer to early universe. If you're modeling it as, where the peak in the 2-point correlation function is. So it is, although it's a low Z measurement, it is in some sense, assuming a lot of early universe. So let me tell you, how much time do I have? Okay. This sounds like a simple thing to do. Okay. In principle, I could rescale the sound horizon by adding a little bit of extra radiation. But this turns out to muck everything up. Let me describe why that's not good. Why this isn't a good solution. So what does extra radiation do just on its own? Let's imagine that you just added an additional neutrino. Or to get an effective of 3.5, you could add an additional neutrino that's maybe just a little bit colder. Contribute a half an energy density of a neutrino. Extra radiation is strongly constrained by the physics of photon diffusion in the early universe. Basic statement here is as photons are scattering around and bouncing around, you can think of them like undergoing some random walk. So the distance that they're diffusing is like the square root of the number of scatters times their mean free path. Okay. This thing scales like square root of time. As a result, you get a rough scaling. This thing goes like time over the mean free path, the number of scatters. So this quantity roughly goes like the square root of the mean free path, which is 1 over the number density of free electrons times the Thomson cross section. This quantity is the mean free path of a photon in the early universe. Also, there's a square root of time sitting in here, which you can think of as giving you a 1 over square root of Hubble for this quantity. Now, once again, you don't measure absolute length scales in CMB, you measure angles. So the corresponding diffusion angle is, instead of the ratio of the sound horizon to the distance of the CMB, it's this diffusion distance over the distance of the CMB, which for a fixed size of the sound horizon, remember, which is RS over the distance of the surface of mass scattering, is just this ratio of distance scales. Diffusion length over the sound horizon. This scales like 1 over square root of Hubble at early times. This scales like 1 over Hubble at early times. So this thing roughly just scales like for a fixed value of the sound horizon. So the statement is, if you tried to add more radiation to be consistent with the larger value of H naught, you would make, for a fixed value of the sound horizon in the CMB, you'd make photons diffuse more. What this ends up doing, if you look at let's say the temperature power spectrum once again. Okay, if you add some extra radiation, it doesn't matter what kind of radiation it is, just really any energy density at early times, you'll start to get washout power. You're going to suppress power. Okay. So for this reason, ineffective of say 3.5 is not a viable solution. Okay, the CME does not allow that. It turns
What
out
L,
that-
roughly what L is this most sensitive to? Because is it really in the CMB or is it post CMB?
It's really in the CMB.
Okay,
So I forget exactly what L, it's an exponential. It's an exponential turn on. I think the diffusion distance is slightly, it's a pretty high scale, so it's pretty high L. I'm gonna guess, I think it's around L of 1,000 or so, where this really becomes a big deal. Physically, you can think of it as coming from the CMB truly, because what this means that photons are diffusing, it means that they're not a perfect fluid. They're not something just described solely by the continuity and Euler equations of fluid mechanics. They don't have just a dipole and a monopole. From free streaming a little bit, because they're able to skip around, they pick up a small quadrupole, and the small quadrupole at the end of the day suppresses power. So it's really something at the end of the day at the level of CMB at early times. Okay, so it turns out that adding extra radiation is additionally bad if you try to add something like a neutrino. So this is an additionally bad reason why you don't want to add so-called free streaming radiation, i.e. radiation that's not a fluid like an extra neutrino. There's an additional effect that comes about, and you can think of this as in position space. Let's think about the radius of some perturbation. Megaparsecs. This is some mass profile of the perturbation. In very early times, inflation just gets you a perturbation and everything. Okay, so this is everything. And you let this perturbation evolve. Well, the dark matter is not going to move much. Okay. The photons are going to move ahead. These are photons, photon perturbations, moving at a velocity of roughly 1 over the square root of 3. This is the sound speed of a perfect fluid. You also have neutrinos, which move even faster. Those perturbations are moving at the speed of light. Okay, dark matter moves at all because these things, dark matter is gravitationally tugged a little bit. But the basic point is that free streaming radiation, like neutrinos, the perturbation, the wavefronts move ahead of the photons. They tug gravitationally on the photons, and they pull the photons out to larger length scales, where this is roughly around 100 or 150 megaparsecs. So this is called the drag effect. You got neutrino perturbations, wavefronts traveling ahead of the photons, pulling them out. What this ends up doing is so free streaming radiation. When you add more of it, like an extra neutrino, this suppresses power even further. It also shifts the it pulls the photon perturbations out to higher distances in L space. L is roughly 1 over an angle on the sky. So if you're going to move a perturbation out to larger distances, you're going to shift your peaks in the CMB to smaller L. So what's going to happen is if you add, just drop here, CMB spectrum, once again, you add free streaming radiation, aside from the fact that I already told you, let's say we kept the diffusion scale fixed. Okay, let's say we're not going to modify that. You just add in free streaming radiation. This is going to suppress things. It's also going to move things to the left a little bit. So these peaks are going to move to the left, and the power is going to be suppressed. Okay, this is an additional constraining artifact of free streaming radiation. For that reason, people have tried playing around with different kind of radiation entirely. Because remember, this statement about ineffective of 3.5 and being consistent with Hubble. is a statement that I just want to increase the energy density at early times, has nothing to do with the type of radiation that I'm adding per se. But we've seen that free streaming radiation has a bad effect on the CMB. So what people have tried adding is instead adding a fluid. By this I mean radiation itself. Okay. This doesn't have the bad effects of free streaming ahead of the photons. A fluid has a sound speed that's roughly the same as photons, roughly 1/√3. So it's going to travel more or less in sync with the photons. It won't pull them out to larger distances. The effect that I was telling you about previously is significantly alleviated if you're adding something like a perfect fluid. It turns out people have done this fit. This used to be a good fit until people considered polarization data. Okay. And if you try to add, let's say, an effective number of neutrinos in fluid of a half.
Yeah. So where does the jarring effect come from? It seems the neutrino have very weak interaction.
It's purely gravitational.
Gravitational.
So the tugging of this on this is only through gravity. So you want to try to add a fluid and add, let's say, a half of a neutrino in fluid on top of the radiation that already exists. You'd say, okay, this would be a way to get a total ineffective of 3 neutrinos plus a little half fluid to be consistent with larger H naught. Dedicated step studies have shown that when you consider high polarization data, which people did originally take into account in their studies, this turns out to not be a good fit.
Is it different from slope damping you mentioned before?
Is it different than what?
Oh, this different effect from
You have the silk damping
Right.
that I was describing before. That is present. What you essentially are doing is you're essentially just living with this. If you added free streaming radiation, you have silk damping and this, which I'll just call a drag effect, like perturbations traveling ahead of the photons. You add fluid, you just have silk damping.
And is it the reason why this high polarization is screwed up, or is that something different?
Is there a reason for it?
Is that
Is that the reason?
Yeah. Is it?
It doesn't seem to be entirely the case because you can essentially undo the silk damping in some sense. Because remember, what I have, the diffusion scale went as square root of Hubble over the Thomson interaction rate. For a fixed baryon density, the number of free electrons goes like 1. It's roughly proportional to 1 minus the helium fraction, because helium is neutral at the time of recombination, so increasing it decreases how many free electrons there are. And people have done studies where they say, I'm just going to allow myself to vary helium freely and add in fluid. And what this does is this allows you to essentially undo this effect. That also turns out not to work. There's some subdominant effects that I haven't told you about, namely the fact that photons don't travel, or sorry, a fluid doesn't travel perfectly in sync with photons because the sound speed of photons is not exactly equal to 1/√3, it's slightly less. So there are additional effects of fluid, and even if you get rid of their effect on silk damping, they're still highly constrained. Okay. So in the last 10 minutes, let me tell you what we did. The fact that high polarization data kills a lot of these models is a motivation to consider something that's null dependent. And then I mean, we're motivated to consider imprints on the CMB that have a null dependent feature. So let me describe you a simple system. Okay. So imagine that you have a fluid that's decoupled From the standard model, it has no direct interactions aside from gravity, but this fluid couples to itself. But unlike what people considered before, it's not just a purely massless fluid. Let's imagine that we have some fermion that's massless and some scalar that's massive. Okay. And these guys interact with each other. Okay, for instance, scatter off of each other. Say, decays, back and forth, inverse decays and decays. Scattering properties as well. So these are really part of the same fluid. But if this guy is massive, what happens is very much how, let's say, at early times, you have photons and electrons, and at late times, you just have photons. At very early times, you're going to start with both of these things in equilibrium with each other. And once you drop below the mass of this massive state in the fluid, you're just going to have psi. Okay. What this means, let's consider the equation of state, W, of this dark fluid as a function of time. At very early times, everything's relativistic. So this equation of state is 1/3. At very late times, only a species that is light enough to be present for a given temperature is psi. This guy has become Boltzmann suppressed at very late times. So at very late times, this thing has an equation of state of roughly 1/3. But in this intermediate regime, when the temperature of the fluid is around the mass of this mediator, the equation of state becomes more like matter, which has an equation of state of 0, and less like pure radiation. Does that make sense? So what this means,
Let's assume there is no asymmetry, I think, assume
there's no
asymmetry in phi.
asymmetry in phi. No, there's nothing like a chemical. Yeah. So what this means, remember things with an equation of state W, redshift like 1/a cubed 1 plus W. So this fluid is going to redshift more slowly than it would have had it been just radiation. What that means is if you ask, what is the number of effective neutrinos in this fluid, which is just defined as the energy density of this fluid divided by the energy density of a single neutrino in the standard level. At a certain, let's say at early times, this is just some number. Okay, dictated by, in some sense, initial conditions of this decoupled fluid. Once I drop below, the temperature of this fluid is around the mass of phi. This system decouples, or sorry, redshifts less rapidly than pure radiation. So compared to neutrinos, gets a gain until it's completely relativistic again. This is because at early times, both of these particles are hanging around. At late times, there's just psi. This is kind of a crucial point. Are there any questions about this step? So this is completely analogous to what happens with photons and electrons. At early times, photons and electrons are part of a fluid. You drop below the electron mass. Electrons dump their entropy into the photons, heat up the photons a little bit. And what people typically talk about is temperature of photons compared to neutrinos after, although this quantity was 1 at very early times, once you drop below the electron mass, this is roughly 11/4 to the 1/3, which you can get from just counting degrees of freedom. Although this is what is usually talked about, this temperature increase also leads to a jump in relative energy density compared to neutrinos. Okay, so once you drop below the electron mass, the contribution of neutrinos to the total energy density compared to photons is suppressed, or the contribution to the energy density of photons compared to neutrinos increases. And this dynamics is essentially the same thing, because the number of effective neutrinos in this fluid is how much energy density is in this fluid compared to a single neutrino, just normalizing energy density. Okay. If you work out the size of this jump, let's say the number of effective neutrinos in this fluid compared to the initial, this is roughly just the effective relativistic degrees of freedom in psi plus the effective relativistic degrees of freedom of phi divided by the psi degrees of freedom over 1/3. So this is something like a two-component spinner. This is something like a complex scalar. This is roughly 1.3. Okay.
So I didn't know, do we need, I assume that psi they also interact with each other? Or
Oh, yeah, yeah. Oh, sure.
because
Sure.
that's the difference with.
Sorry, I forgot to mention that. Thank you. So at late times, all these interactions are on the early times. Everything's relativistic. As you drop below the mass of phi, it's integrated out. It's something like a 4 Fermi interaction among psis. In this model, these interactions are strong to keep this thing a fluid, provided that the mass of phi is much lighter than MEV. If he's at an MEV, you need order 1 couplings. And this is just the statement that you want this thing to be strongly coupled down to the time of recombination, down to an EV. So if you want this to be, what we're going to have in mind, in fact, is a little jump that happens around 10 EV. When the temperature of the photon is around 10 EV, so it matters from the point of view of CMB. So we're going to imagine that this guy has a mass of around 10 EV. Okay. And that motivates couplings roughly at the level of 7-5 or bigger to keep these interactions important.
So how do you determine initial condition of the psi-phi fluid? Because it's also constrained by effect.
It is constrained by an effective, so it is essentially a model input, but it can't be too big. So, if it's less than, let's say 1, it's not going to be ruled out, for instance, from, let's make it smaller than 1/2, be more strict. If it's smaller, if it is smaller than 1/2, it's not going to be ruled out from primordial nucleosynthesis. It's not going to be ruled out from BBN or anything like that. In fact, I want to tell you quickly in the next minute is how this actually is good, how the CMB actually wants this. Okay. So what I want to compare is this model where I step up. So that's the camera work. I want to compare this model. So I have some number of effective neutrinos in fluid where it steps up just due to thermodynamics. I want to compare this to a model that never had the step, it was just always there. What's the difference between these two models? Okay, keeping the late time physics fixed, it's not only the late time physics that's most important for the CMB. This is kind of the most meaningful comparison. When you do this, when you do this, if you ask what is the shift to the L position of some peak in the CMB as a function of the peak position, the CMB looks something like this. So we're going to ask what happens to the peaks when I give a model a step as opposed to a step that never existed. For very low L modes, okay, these are perturbations in the CMB that entered the horizon very late. So for very low modes, these things enter the horizon after the step has occurred, and they don't see the fact that there was a little bit of a deficiency at earlier times. So that in comparison of this model and this model, modes that enter very, very late into the horizon don't care about the fact that the step occurred. So there's zero residual. But as I talk about higher and higher L modes, these are things that entered the horizon before the step happened, so they can distinguish between these two models. What ends up happening as you go, these are different positions of this step. This is roughly controlled by the mass of phi. Okay, as you go here, move this direction. These are later steps in the CMB, and what they do is they put in a feature. There's essentially they don't have time. There's essentially, I don't have time to tell you why, but these things shift the peaks in the CMB towards smaller L, okay, larger angular scales. For high L modes that enter the horizon to distinguish between these two models, modes that enter very late can't distinguish between these two models and see no residual. So this is an L-dependent feature that isn't degenerate with any lambda CDM parameters. And what we find, just an upshot, is lambda CDM has a tension, let's say with shoes, of roughly 4.5 sigma. Lambda CDM, if you add a little bit of, let's say, an extra neutrino, that's been studied. That reduces the tension to roughly 4 sigma. If you think of a better model, this is lambda CDM plus a fluid, just a normal fluid. This reduces the tension to around 3 sigma. Then if you finally do the thing that we did, which is lambda CDM plus this step fluid, this brings it down to around 2 sigma. There are additional details of the fit that I don't really have time to talk to you about. It turns out the CMB, in fact, just likes this feature independent of anything having to do with shoes. You see, let me just forget about all the H-naught determinations. Let me just ask the CMB, DAO, these kinds of things. Are these features, does the CMB like this? Does the CMB want to have it? There's a mild preference for the step to exist. And in fact, at the CMB alone, there's a preference for this radiation to be present that is different from no radiation, that's distinguishable from no radiation at the level of 90% confidence. And when you put in a shoes value, of course, when you put into your data set to what you're fitting, these late time determinations in H-naught, of course, the predicted value of H-naught increases, but this preference for some fluid being present is relatively unchanged. So I'll just end there and answer any questions. Yeah.
So
Yeah.
So if you were to use this preference of the CMB alone to fit the parameters, how close would you get to the best fit? How much would it reduce sigma?
So this is essentially this value.
Okay, so you're not trying.
So yeah, here when I'm telling you these values, I'm saying essentially doing a fit, not with no inputs about late time determinations of H-naught, and then I can reconstruct some posterior for H-naught from that model without informing the fit about shoes. And that's what these numbers are. So it brings it down to, it prefers a higher value H-naught, brings down the tension level 2 sigma without any inputs into the model.
Is there input at which value of L you put a step? Or
So yeah, so that's essentially this model is a two ingredient model. We have how much radiation is present at, let's say, you can either fix how much radiation is present at early times or how much radiation is present at late times. These two things are not independent because they're just related by this ratio. But you choose, let's say you choose how much radiation is present at late times, and that's one of your dials that you're turning. The other dial that you're turning is the position of this jump. And so it's extending the lambda CDM by 2 inputs. And that being said, when you ask what's the chi-squared with shoes, the total chi-squared of your best fit, including shoes in the data set, it decreases the chi-squared compared to lambda CDM by around -15 with the addition of 2 single parameters. And if it wasn't doing anything, the normal expectation is just 1 per degree of freedom if you're already starting with a good fit. So it looks like it's doing something more other than just adding in new knobs.
perturbations in this fluid important because
Yeah.
it goes with a step where it's like not radiation, but like
Yeah,
like
exactly.
matter, probably there's
So
some
I erased
power
it.
there.
I erased it. So in fact, I just talked about a background quantity, which is how W changes, but there's also the sound speed. And that enters with a little perturbations. And it lags behind a little bit, but it has a similar feature. And the perturbations are important. So it's not purely a background quantity. It's not just about energy density, it's also about the perturbations in the fluid, which we modeled as well.
So we can keep talking, but I just want to, let's thank Asher again and give you a chance to give that answer. I think there are a lot more questions. So.
What is the Z and L values like for that visual factor?
The best fit